And welcome to the Biochemistry Blockbuster segment. I'm your host, Ayana Sandoval, but you can call me Yana. Today on the show, we have an action-packed live show for you all today. We sit back, relax, and enjoy.
I'm a patient diagnosed with type 2 diabetes. Insulin is a hormone that regulates the movement of sugar into your blood cells. Or the pancreas doesn't produce enough insulin to maintain a normal glucose level. The tablet that I take to regulate my blood glucose level is called metformin. Metformin works by suppressing gluconeogenesis. This occurs by the metformin inhibiting the ATP production of the mitochondrial respiratory chain. Mitochondria is a small organelle within the cell that produces ATP from ADP. ATP is the energy currency of our body. We also get energy from a process that is called glycolysis. Glycolysis is the breaking down of glucose molecules to produce energy, but this provides a little bit of energy. The glucose of glycolysis produces two pyruvate molecules which enter the mitochondrial respiratory chain and is burned, which releases more energy. This gives off carbon dioxide and water. Metformin interferes with the ADP to ATP ratio by decreasing. When this ratio of energy is decreased, this inhibits the first bypass reaction of gluconeogenesis, which is catabolized by pyruvate carboxylase. Pyruvate carboxylase, which is known as an ABC enzyme, uses ATP to drive it by inhibiting the first bypass reaction of gluconeogenesis. New sugar will not be made. So this is how metformin regulates blood glucose level. And well, as I said before, I use it along with exercise as a balanced diet.
Well, I must say congratulations because for your diagnosis you look absolutely stunning.
Thank you very much.
Well, it was nice having you on the show. Have the world famous fitness instructor, Miss Linda O'Neill, who are into fitness. I can't say. Hi, welcome.
We are all into fitness, but we don't really know like chemicals, what really happens in the body, like in the muscles during fitness. And today I'm going to talk about the Cori cycle and anabola. If we have to exercise during muscular activity, epinephrine is released by the adrenal medulla. This is a chemical that stimulates the adrenalizes in muscles.
famous author. So what's up?
Explaining how alcohol affects lipid metabolism.
Okay.
So here's another top right now.
Okay, so director, let's go straight to the video.
And did you know alcohol cannot be stored as oxidized in the liver alone? When you drink like me, alcohol means activated energy, which leads to malnutrition. Because alcohol ain't got no minerals, no vitamins, no carbs, no proteins. No minerals, no vitamins, no carbs, no proteins. It makes your NADH, NAD plus ratio flicker, flicker, flicker. Alcohol dehydrogenase needs NAD plus to catalyze ethanol to acetaldehyde plus NADH in the liver. Aldehyde dehydrogenase needs NAD plus to catalyze acetaldehyde to acetic acid plus NADH in the mitochondria. And that's the problem with drinking a little bit of liquor. It makes your NADH, NAD plus ratio flicker, flicker, flicker. Pour up, drink, headshot, drink, sit down, drink, stand up, drink, pass out, drink, wake up, drink, faded, drink, faded. Alcohol tastes like morphine to my brain. I'm addicted. But how did it end up this way? It started with one drink. Or maybe two. I don't remember. Do you? When you drink too much, meals kicks in, meals kicks in, meals kicks in. CYP2E1 is the main enzyme. It's crazy. It turns Tylenol toxic. It's crazy. Contributes to NAFLD, NASH, hypolipidemia, type 2 diabetes, and obesity. But wait. More alcohol, more CYP2E1, more acetaldehyde in the brain. Acetaldehyde reacts with neurotransmitters to form morphine-type compound. Pour up, drink, headshot, drink, sit down, drink, stand up, drink, pass out, drink, wake up, drink, faded, drink, faded. Alcohol tastes like morphine to my brain. I'm addicted. Flicker, flicker, flicker. Fatty acids are reesterified into TAGs by combining with G3P. TAGs turn to VLDLs that accumulate in the liver. That enters the blood. Who say hyperlipidemia? Now take it back real quick. More alcohol means meals. Meals induces acetyltransferases, which makes tags in the ER, which leads to hepatic steatosis. Whew. I'm tired. But hey, do you know about alcohol-induced ketoacidosis? All the NADH prevents ACOC from entering TCAC, and said ACOC makes ketone bodies, and we call that ketoacidosis. And notice, still
I'm sure you are familiar with the name Biochemistry. He is one of the research lecturers within around UB an award for his work done at UB. So, he cannot be here with us today, but he sent us for an amazing topic in biochemistry. Now, I'll give to you Biochemistry.
Hi guys, I'm Jason Matthew from Trinidad and Tobago, and today we are going to do a tutorial on glycolysis and gluconeogenesis. Now when we hear the word glycolysis, we should immediately know that gly means glucose and lysis means split. So overall, glycolysis is the splitting of one molecule of 6-carbon sugar glucose into 2 molecules of 3-carbon tyrosine. Glycolysis takes place in the cytosol, and there are 2 phases to this reaction: an energy investment phase and an energy generation phase. The energy generation phase produces 2 ADPs, and this involves 1 irreversible reaction and 4 reversible reactions. From the chart, we can see that 10 enzymes are involved, with the enzyme being PFK1. The most frequently asked question is gluconeogenesis, the reverse of glycolysis. Now, what is gluconeogenesis? It is a process where glucose is made from non-carbohydrate sources. This happens in a fasting state. It takes place both in the cytosol and the mitochondria. Now, firstly, in gluconeogenesis, 11 enzymes are involved. 4 unique enzymes and 7 common to glycolysis. Hexokinase is replaced by glucose 6-phosphatase, PSK1 is replaced by fructose 1,6-bisphosphatase, and pyruvate kinase is replaced by pyruvate carboxylase and PEPCK. In the first bypass reaction, pyruvate and carbon dioxide is converted into oxaloacetate. The oxaloacetate is unable to leave the mitochondria because the membrane is impermeable to it. So another reaction follows where oxaloacetate is converted into malate. The malate leaves the mitochondria and enters the cytosol, where it is then converted back to oxaloacetate, which is further converted into PEP. The second bypass reaction is when fructose 1,6-bisphosphate is converted to fructose 6-phosphate, with the enzyme being fructose 1,6-bisphosphatase. The third bypass reaction is where glucose 6-phosphate is converted to glucose in the presence of glucose 6-phosphatase. 4 ATP is consumed and 2 GTP. Therefore, 6 triphosphates are consumed in total. So in summary, glycolysis takes place in the cytosol, while gluconeogenesis takes place both in the cytosol and the mitochondria. At the end, glycolysis consumes 2 ATP, while gluconeogenesis consumes 4 ATP and 2 GTP. And most importantly, glycolysis has 3 non-reversible enzymes: hexokinase, PSK1, and pyruvate kinase, while gluconeogenesis has 4 non-reversible enzymes: pyruvate carboxylase, PEPCK, fructose 1,6-bisphosphatase, and glucose 6-phosphatase. As a result, gluconeogenesis is not the exact reverse of glycolysis. Okay, thank you very much guys for listening, and don't forget to like and subscribe to my YouTube channel, Biochem JS. Thanks.